The universe contains 2 trillion galaxies. Not 2 billion, 2 trillion. Each one carrying hundreds of billions of stars. And around those stars, planets. Rocky ones, watery ones, ancient ones that formed long before our sun was even a cloud of gas. By every calculation we have, by every model, by every telescope pointed at the sky, the conditions for life should exist in countless places. Chemistry works the same way everywhere. Physics doesn't take days off. The ingredients are not rare. And yet, complete, absolute silence. Not a whisper, not a blip, not one confirmed signal from anywhere out there. The most crowded universe imaginable, and it sounds like an empty room. That silence has a name. Physicists call it the Fermi Paradox. And if you've never heard of it, what you're about to learn is going to change how you look at the night sky forever. Not because it's frightening, though parts of it are, but because it forces a question that science still cannot answer. Where is everybody? If you've been with this channel for a while, you already know we don't do easy answers here. We go deep. So if this is your first time, welcome. Hit subscribe and stay close, because this one goes places most science videos don't dare to go. In 1950, Enrico Fermi visited Los Alamos National Laboratory in New Mexico. He wasn't there for alien theories. He was the winner of the 1938 Nobel Prize in Physics, the man who led the team that built the world's first nuclear reactor, a key contributor to the Manhattan Project. He was one of the sharpest analytical minds of the 20th century, a man famous for asking questions that sounded simple but weren't. Walking to the Fuller Lodge for lunch, he'd been talking with fellow physicists Emil Konopinski, Edward Teller, and Herbert York about reports of flying saucers. When the conversation shifted to other topics at the table, Fermi blurted out a question variously remembered as, "Where is everybody?" The table went quiet. 3 people who were part of that discussion later reported that Fermi was specifically talking about interstellar travel. If aliens exist and are capable of flying between stars, they should have visited us already. He wasn't writing a paper. He wasn't presenting at a conference. He was eating lunch. And in a few seconds of offhand calculation, he had crystallized the most uncomfortable question in modern science. Fermi began working through a series of calculations on the probability of Earth-like planets, the probability of life given an Earth, the probability of humans given life, and the likely rise and duration of high technology. Together, they concluded that we ought to have been visited a long time ago, and many times over. But they hadn't been. And that gap between what the math predicts and what we actually observe is the paradox. Fermi never published any work on his off-the-cuff remark and died just 4 years later. The story of the Fermi Paradox and the lunchtime conversation that started it existed as a kind of urban legend in the Los Alamos community long after his death. In 1984, physicist Eric Jones at the laboratory wrote to the 3 surviving members to capture their recollections, and that forms the basis of our understanding today. 1 man, 1 lunch, 1 question, and 75 years later, we still don't have an answer. Now, before we get into what the silence might mean, let's understand why the silence is so strange to begin with. Because it's easy to say, space is big, of course we haven't found anything. That's not actually the argument. The argument is much sharper than that. The Milky Way alone is estimated to contain between 100 and 400 billion stars, and at least that number of planets. In November 2020, over 300 million habitable exoplanets were estimated to exist in our galaxy. 300 million worlds where liquid water could sit on a surface, where chemistry could begin. where something could crawl out of a primordial soup and eventually look up. And our galaxy isn't young. It's been around for roughly 13 billion years. Earth is 4.5 billion years old. That means there were stars forming, planets cooling, and conditions ripening for life long before our sun even existed. Some of those worlds had a head start on us of 1 billion years. Some had 2 billion. The universe didn't wait for us to arrive before getting started. Close your eyes for a second and think about what that means. A civilization that got going just 1 million years ahead of ours. Not 1 billion, not even 100 million, just 1 million. Would have had time to develop technology we can't even conceptualize. Our entire recorded history is less than 10,000 years old. In 1 million years, starting from where we are right now, where would we be? What would we have built? Where would we have gone? The galactic colonization timescale, the time it would take a spacefaring civilization to spread across the Milky Way, is roughly 100 million years. The age of our galaxy is 13 billion years. That means even a slow-moving civilization would have swept across this galaxy like wildfire, viewed on galactic timescales. Being really pessimistic, the entire galaxy can be explored in less than 300 million years, far shorter than the galaxy's lifetime. And that's with conservative assumptions. Ships moving at Voyager speeds, long pauses between settlements, no technological improvement. Even then, the galaxy fills up in a sliver of its total age. So when physicists talk about the Fermi Paradox, they're not saying, shouldn't we have picked up a radio signal by now? They're saying something much more extreme. If even one civilization in our galaxy had reached interstellar capability at any point in the last 1 billion years, we should see evidence of it everywhere. In the structure of star systems, in artificial megastructures blocking starlight, in self-replicating probes seeding the galaxy, in something. Nothing. Not a single confirmed trace. And that is what makes the silence so loud. The first serious attempt to put numbers to this problem came 11 years after Fermi's lunch. Not from a philosopher, not from a science fiction writer, from a radio astronomer sitting at a telescope, trying to figure out how to have a productive meeting. Frank Drake made the first systematic search for extraterrestrial signals at the National Radio Astronomy Observatory in Green Bank, West Virginia. A project called OSMA. Using the observatory's dish, he monitored 2 nearby sun-like stars, Epsilon Eridani and Tau Ceti, scanning radio frequencies for 6 hours a day from April to July of 1960. It detected no signals. But the attempt had lit something in the scientific community. In 1961, just 1 year after Drake's Project OSMA was completed, a conference was held at the Green Bank Observatory on the topic of extraterrestrial intelligent life, specifically examining whether the ongoing searches had any realistic chance of detecting a real signal. About a dozen people attended this informal meeting, and they were all eminent. Among them was biochemist Melvin Calvin, who received a call during the meeting notifying him that he had just won the Nobel Prize. Biologist Joshua Lederberg, physicist Philip Morrison, and a young planetary astronomer named Carl Sagan. Sagan was 27, the youngest in the room, one of the least decorated names on the guest list.
He would later become the most famous.
In preparation for this meeting, Drake prepared the equation that would come to bear his name. The story is almost funny in its practicality. While planning the event, Drake chose to organize the discussion around a simple formula he concocted that estimated a critical number, the count of transmitting worlds in the galaxy. He needed an agenda, so he built one out of the universe. On the 1st of November, 1961, after the guests were seated and sipping coffee, Drake wrote on a chalkboard, N equals R star times FP times NE times FL times FI times FC times L. That string of letters has come to be known as the Drake equation. What does it mean? Let's walk through it, because the equation is both more brilliant and more frustrating than it first appears. N is the number you want. How many civilizations in our galaxy are currently sending signals we could detect? To get there, you multiply together a chain of probabilities. How many new stars form each year? What fraction of those stars have planets? Of those planets, how many sit in the right zone for liquid water? Of those, how many actually develop life? Of those with life, how many evolve intelligence? Of those intelligent species, how many develop technology that broadcasts into space? And finally, the number that breaks everything. How long does that civilization continue broadcasting before it goes quiet? The purpose of the equation was not to calculate a precise value, but to promote productive discussion. Drake's original estimate was optimistic, suggesting there were somewhere between 10 and 10,000 advanced civilizations in the Milky Way. That sounds like a lot, but here's where it gets genuinely unsettling. Drake himself stated that given the uncertainties, the original meeting concluded that N roughly equals L, the lifespan of a civilization in years, and that there were probably between 1,000 and 100 million planets with civilizations in the Milky Way. 100 million. That's how optimistic you can get if you assume life arises easily and civilizations last a long time. But here's the problem with the Drake equation. It's a framework, not an answer. Most of the variables in it are essentially guesses. In fact, since 1961, we've made little progress in pinning down most of the terms, apart from the fraction of new stars with planets, and to a lesser degree, the number of habitable planets per system. The first few variables, star formation rates, the fraction of stars with planets, we know reasonably well now. Based on Kepler Space Telescope data, there could be as many as 40 billion Earth-sized planets orbiting in the habitable zones of Sun-like stars and red dwarf stars within the Milky Way alone. 40 billion. 40 billion potential Earths in just our galaxy, circling at just the right distance from their stars. But then you hit the biological variables. What fraction of those worlds actually develop life? What fraction of life becomes intelligent? These numbers are not guesses dressed up as science. They are genuinely, honestly, deeply unknown. We have exactly one data point, Earth. And one data point tells you almost nothing about a probability. Fill in the equation with pessimistic numbers, and n equals 1. We're alone. Fill it in optimistically, and n equals millions. The equation is like a lock, where you don't know the combination. It can open any door depending on what you put in. And that ambiguity is not a bug. It's the whole point. Drake built the equation to force scientists to be honest about what they didn't know. What they didn't know in 1961. What they still largely don't know today. So let's sit with the scale problem for a moment, because I think it's easy to hear billions of stars and let the enormities slide off without really landing. The Milky Way has a diameter estimated at roughly 87,000 light-years. Light, the fastest thing in the universe, covering 300,000 kilometers every single second, would take 87,000 years to cross our galaxy from edge to edge. That's longer than modern humans have existed. That's longer than any recorded civilization by a factor of almost 10. And our galaxy is one of 2 trillion. The observable universe, the part we can theoretically see, contains structure that took 13.8 billion years to form. Stars that have already lived and died before our sun was born. Worlds that had billions of years of head start on complex chemistry. Now stack that against what we know about colonization math. At just 1% of the speed of light, which is roughly 3,000 kilometers per second, far faster than anything we've built, but not absurdly so for a hypothetical spacefaring civilization, you could cross the Milky Way in about 10 million years. 10 million years.
In a galaxy 13 billion years old, that is less than 0.1% of cosmic history. Even with very conservative limits placed on ship speed, a majority of the galaxy could be colonized in less than 1 billion years, a fraction of its total age. Think of it this way. If the Milky Way's history were compressed into a single calendar year starting on January 1st, Earth doesn't even form until late September. And the window in which a civilization would need to have existed, anywhere in the galaxy, using any reasonable technology at any point, to have filled the whole place up with signals and artifacts by now? That window opened in early February and never closed. We should have seen something by now. We should have collided with something by now. The silence isn't just surprising, it's statistically screaming at us. And that scream is exactly what Robin Hansen tried to answer. The idea was first proposed in an online essay titled, "The Great Filter. Are We Almost Past It?" The first version was written in August 1996. Hansen wasn't an astrophysicist, he was an economist. And he approached the problem the way an economist would, not by pointing a telescope at the sky, but by working backward from what we observe. The Great Filter is a hypothesis in astrobiology and futures studies proposing that the evolution of life from simple replicators to expansive interstellar civilizations must pass through one or more extraordinarily improbable barriers, dramatically reducing the number of advanced societies that emerge across the universe. The argument is almost elegant in its brutality. You start with the fact that the universe is vast and old, and filled with the raw materials of life. You run the numbers and conclude that advanced civilizations should be everywhere. You look up. Nothing. So somewhere between dead matter and galaxy-spanning civilization, something goes catastrophically wrong. Almost always. For almost everyone. That something is the filter. The Great Filter says that intelligent interstellar life forms must first take many critical steps, and at least one of these steps must be highly improbable. The premise is that there is at least one hurdle so high that virtually no species can clear it. Picture 100 million worlds where life starts, maybe 1 billion, each one working through the checklist: single-celled life, complex cells with a nucleus, multicellular organisms, nervous systems, intelligence, language, technology, spaceflight. Each step takes millions or hundreds of millions of years, and somewhere in that chain, there's a door that almost nothing gets through. The question isn't whether the filter exists. Hansen himself stated, "This one data point implies that a great filter stands between ordinary dead matter and advanced, exploding, lasting life. And the big question is, how far along this filter are we? How far along are we?" That's the question. And it splits into the two most different futures imaginable. The probability threshold could lie in the past, meaning something we've already survived, or lie in our future, connected to how civilizations destroy themselves. If the filter is behind us, we are extraordinarily lucky. Life arising from chemistry, truly randomly improbable. Or the jump from simple cells to complex ones, which on Earth took nearly 2 billion years
and may have happened exactly once through a collision so specific it looks like an accident of cosmic proportions. If that transition is the filter, then the universe is full of bacterial worlds, planets covered in microbial life that never goes anywhere. Bacteria don't build telescopes.
Maybe the universe is teeming with bacteria, but bacteria don't build starships. In that case, our silence is good news. We made it through. We are, statistically speaking, a miracle. But if the filter is ahead of us, then it means civilizations routinely get to roughly where we are, and then something ends them. Nuclear war, climate collapse, a pandemic they couldn't contain, an artificial intelligence that turned against them, a technology that every advanced species eventually discovers and that every advanced species eventually misuses. Something inevitable, something waiting. The main conclusion of this argument is deeply counterintuitive. The more probable it is that other life could evolve to the present stage in which humanity is, the bleaker the future chances of humanity probably are. Read that again slowly. The easier it was for us to get here, the more common life and intelligence turn out to be, the worse our odds. Because if the hard step is behind us, we're rare. If the hard step is ahead of us, we're just the next in line. This is why philosopher Nick Bostrom made a statement that sounds completely backwards until you understand the logic. He said he hopes we find nothing on Mars. Nothing. Dead rocks, sterile soil, lifeless ice. As he wrote, "It would be by far the worst news ever printed on a newspaper cover to find complex life on Mars." This is why I'm hoping that our space probes will discover dead rocks and lifeless sands on Mars, on Jupiter's moon Europa, and everywhere else our astronomers look. Finding life independently evolved on Mars would suggest that the emergence of life is not a very improbable event. If it happened independently twice here in our own backyard, it must surely have happened millions of times across the galaxy. This would mean that the Great Filter is less likely to occur in the early life of planets, and therefore more likely still to come. The news that life exists somewhere else in the solar system would be the greatest scientific discovery in human history. It would also be, quietly, a death sentence for our long-term future. Now, there's a fresh angle on all of this that only arrived in the last few months. In February 2026, two physicists from Sharif University of Technology in Tehran published a paper that tried to put a hard number on something the Fermi Paradox had always left fuzzy. Not where the filter is, but how long civilizations typically last. In their work, Sohrab Ravar and Shaheen Rouhani explored constraints on the emergence and longevity of technologically intelligent civilizations in our galaxy. They argued that under optimistic assumptions about the probability of life and intelligence emerging on Earth-like planets, the absence of contact with extraterrestrial civilizations imposes limits on their lifespan. Their analysis of the Fermi Paradox suggests that if intelligent life is common, the absence of detectable signals implies that technological civilizations typically last no more than about 5,000 years. 5,000 years. That's not a long time. That's roughly the age of the oldest written records on Earth. That's the span from the first Sumerian cities to right now. If the math is right, if life is common and we still hear nothing, then somewhere between inventing writing and learning to send signals into space, something ends, almost everyone. The authors emphasized that this is not a prediction, but a constraint derived from the Fermi Paradox. Human civilization currently has the means to destroy itself within centuries, far below this bound. We are, at this very moment, somewhere inside that window. There's one thing worth noting here before we go any further. The Great Filter isn't a single moment.
It's a metaphor for a probability. In a subsequent paper, Hansen constructed a simulation suggesting there should be about 4 to 7 hard steps in our evolutionary past, distributed across our history, not concentrated in one dramatic moment. Think of it like a series of locked doors along a very long corridor. Each door is hard to open. Most lines of life never get through the first one. A smaller number make it to the second. Fewer still reach the third. By the time you're at door 7, by the time you've got brains and language and fire and cities, the number of species that have made it this far might be 1. Might be us. Or there's one more door ahead. The origin of the eukaryotic cell, the kind of cell every complex organism on Earth is built from, took nearly 2 billion years to appear after simple life began. 2 billion years of bacteria going nowhere. And then, somehow, one bacterium absorbed another instead of digesting it, and the absorbed one stayed and became the mitochondria, and everything changed. Astrophysicist Matt O'Dowd has identified this transition, eukaryogenesis, as a reasonable candidate for a great filter in the past, given the increasing difficulties in finding new, useful proteins for prokaryotes. That transition happened once on Earth, as far as we know, once in 4 billion years. If it happened once here, how many worlds are stuck before that door, covered in bacteria that have been sitting there for 1 billion years, not because they're unlucky, but because the next step is astronomically improbable? Maybe the universe is an ocean of microbial life, and we are the only fish. But wait, that's only one half of the Great Filter story, because there's an equally disturbing set of candidates that don't require the hard step to be behind us at all. Candidates that suggest the most dangerous moment in any civilization's existence is precisely when it gets smart enough to be dangerous. One potential location for the Great Filter involves technological self-destruction, where advanced civilizations develop capabilities that enable their extinction before achieving sustainable interstellar expansion. Nuclear war represents a prominent risk, as evidenced by near misses such as the 1962 Cuban Missile Crisis, during which a Soviet submarine commander nearly authorized a nuclear torpedo launch amid miscommunications. We came within one person's decision of ending our civilization in 1962. One man, on a submarine, with no communication to the surface, in a moment of panic and incomplete information. He didn't press the button. But it was close. If that kind of moment happens to every civilization that develops nuclear weapons, and if every civilization that develops the physics to split an atom also develops the ambition to weaponize it, then the filter might be sitting right there, at the intersection of knowledge and aggression. The very moment a species becomes capable of reaching the stars, it also becomes capable of ending itself. Similarly, artificial intelligence misalignment could lead to catastrophic outcomes if superintelligent systems pursue goals incompatible with human survival, a concern emphasized in analyses of existential risks where AI development outpaces safety measures. Or maybe it's something we haven't named yet. A technology so transformative that it disrupts civilization before civilization can adapt to it. Something that every species discovers on roughly the same developmental timeline, because physics is universal, and that every species mishandles at approximately the same developmental stage. The terrifying logic of the Great Filter is that it doesn't care what the mechanism is. It only requires that something, somewhere in the chain, almost always wins. And the silence tells us it does. There's a version of this that's even harder to sit with. Not that civilizations get wiped out, but that they get to some threshold, some level of technological and cognitive development, and then choose, or are forced, to go quiet, to stop broadcasting, to stop expanding, to turn inward in ways that make them invisible to anything looking from the outside. Astrobiologists reviewing the history of life on Earth, including convergent evolution, concluded that transitions such as oxygenic photosynthesis, the eukaryotic cell, multicellularity, and tool-using intelligence are likely to occur on any Earth-like planet given enough time. They argue that the great filter may be abiogenesis, the rise of technological intelligence, or an inability to settle other worlds because of self-destruction or a lack of resources. What this means, in plain language, is that even among scientists who study this professionally, there's no consensus. The filter could be at the very beginning of life. It could be at the very end.
It could be multiple filters, stacked. The math is consistent with all of them, and that consistency is precisely what makes the question so persistent. We can do the counting. We can calculate the colonization timescales. We can measure the age of the galaxy and the number of habitable worlds. And every time we do, we arrive at the same conclusion. There should be someone out there, and there isn't. Or if there is, they're silent in a way that itself requires an explanation. The numbers keep pointing at the same wall. The question is whether the wall is behind us or whether we're walking toward it right now, carrying the very tools that will, one day, build it. That question, are there explanations that don't require disaster, sits at the center of everything that follows. Because not every answer to the Fermi Paradox ends in extinction. Some of them end in something stranger, something that, depending on your temperament, is either more comforting or more disturbing than death. The easiest answer to the Fermi Paradox is also the most quietly unsettling one.
Not that they're dead, not that they never existed, but that they're out there, watching, and have decided, for reasons of their own, to say nothing. This idea has a name. Astronomers call it the zoo hypothesis, and the man who first gave it a scientific framework wasn't a fringe theorist or a science fiction writer. He was a mainstream astrophysicist at Harvard. John Ball published a paper in 1973 in the journal Icarus, a respected peer-reviewed publication titled The Zoo Hypothesis. His argument was precise and troubling. If extraterrestrial intelligences exist and are sufficiently advanced, they may have deliberately chosen not to contact us, much as we deliberately avoid disturbing animals in a zoo or wildlife preserve. The choice wouldn't be hostility, it wouldn't be indifference, it would be policy.
A decision made at a civilizational level to leave us alone until, or unless, we reach some threshold they've defined as worthy of contact.
Ball didn't dress this up in drama. He laid it out as a logical possibility, derived from the same premises as the Fermi Paradox itself. If civilizations exist and are old enough, they've had time to observe us for millions of years. They've watched us go from stone tools to nuclear reactors in a geological eye blink. And they're still quiet. Not because they can't reach us, but because reaching us isn't what they want to do yet. What makes this hypothesis genuinely uncomfortable isn't the idea of being watched. It's the implication of the threshold. What are they waiting for? Some level of technology? Some demonstrated ethics? The fact that we haven't destroyed ourselves yet? Some proof of cooperative behavior at a planetary scale? We don't know. We can't know, because the criterion is theirs, not ours.
And until we meet it, the silence continues, regardless of how many telescopes we point at the sky.
There's a refinement of this idea sometimes called the interdict scenario, proposed by researchers in the 1980s, suggesting that the zoo isn't passive. There may be an active, enforced quarantine, a kind of interstellar agreement, not just one civilization staying quiet, but all of them, by consensus or by law, maintaining a perimeter around developing worlds. Under this model, the first contact isn't something we'll achieve by broadcasting. It's something granted to us. Or not. If that sounds too sci-fi to take seriously, consider what we actually do here on Earth with uncontacted peoples. There are still isolated indigenous groups in the Amazon and in the Andaman Islands who have no connection to the modern world. Multiple countries have legal frameworks protecting those populations from outside contact.
There are researchers, anthropologists, satellite surveyors who know exactly where these groups are and maintain a deliberate, legally enforced silence. Not because the people are dangerous, because contact on unequal terms causes harm that can't be undone. We built the zoo. We're running it right now. Scaling that idea up to interstellar distances isn't a leap of imagination. It's an extrapolation of something we already do. The zoo hypothesis is comforting in its way. At least someone is watching. At least someone is there. The dark forest is not comforting. The name comes from a novel by Chinese science fiction author Liu Cixin, the second book of his three-body problem trilogy, published in 2008. But the idea behind it had circulated in scientific and philosophical discussions before it became a cultural phenomenon through fiction. The basic logic was captured in various forms by researchers thinking about game theory and interstellar strategy long before Liu gave it its now famous name. The argument is this: the universe has finite resources. Life requires energy and matter. Any civilization advanced enough to expand through the cosmos knows this, and knows that any other civilization it encounters is a potential competitor for those same resources. Communication is dangerous because it reveals your location. Interaction is dangerous because you cannot verify the intentions of an alien mind. You cannot know if they are friendly. You cannot know if they are lying when they claim to be friendly. And the consequences of being wrong are extinction. In a universe where every civilization faces this calculus, the rational strategy is silence. Go dark. Don't broadcast. Don't respond to signals. And if you detect another civilization that is broadcasting, eliminate it before it can grow large enough to become a threat. Not out of malice, out of pure survival logic. Liu put it this way in the novel: the universe is a dark forest. Every civilization is a hunter with a gun, hiding in the woods, moving carefully, pushing aside branches and treading lightly, even breathing quietly. The hunter has to be alert, because everywhere in the forest are stealthy hunters like him. If he finds another life, another hunter, angel or demon, healthy or diseased, good or evil, he can only do one thing: open fire and eliminate them. This isn't just fiction. Physicist and science communicator Milan Cirkovic and others have discussed in academic publications the strategic logic of asymmetric information in interstellar contact scenarios. The dark forest is a hypothesis with real game-theoretic grounding. If the cost of being wrong about a stranger is civilization ending, and you can't verify their intentions, and they know you can't verify their intentions, then contact is not just risky, it's irrational. The dark forest theory produces an immediate and deeply personal implication. Every signal we've ever broadcast, every television transmission that has leaked into space, every deliberate message we've aimed at stars, every radar pulse bounced off the ionosphere, is a flare fired into a forest full of armed hunters. SETI, the search for extraterrestrial intelligence, searches for signals. METI, messaging extraterrestrial intelligence, sends them. And some physicists think METI is the most dangerous thing we could be doing. Stephen Hawking was explicit on this point. In his 2010 documentary series, he said, "If aliens visit us, the outcome would be much as when Columbus landed in America, which didn't turn out well for the Native Americans." He wasn't dramatizing.
He was applying exactly the same logic as the Dark Forest, that the history of contact between civilizations with unequal technological power is a history of the weaker one losing.
In 2015, a group of scientists signed an open letter calling for a moratorium on active messaging to extraterrestrial intelligence. Among the signatories were Hawking himself and a group of SETI researchers who were uncomfortable with the philosophical direction. The argument wasn't that aliens are hostile. It was that we don't know they aren't, and broadcasting our location before we understand the landscape might be the last thing we ever do. A counter-argument exists, and it's worth giving it a fair hearing. Astrophysicist Seth Shostak at the SETI Institute pointed out that Earth has been leaking electromagnetic radiation into space since the early 20th century. Any civilization within roughly 100 light-years already knows we're here. The ship, as he put it, has sailed. Staying quiet now is like closing the barn door after 100 years of horses walking out. Both arguments are correct in their own frame, and that tension, do we shout or do we hide, is real, active, and unresolved. There is no consensus. There is no policy. We are currently doing both simultaneously, somewhat accidentally, without having decided what we actually want the answer to be. There's one more hypothesis in this family that deserves its moment, because it goes somewhere darker than the zoo and stranger than the dark forest. It's called the planetarium hypothesis. Proposed by British physicist Stephen Webb in his 2002 book, If the Universe is Teeming with Aliens, Where is Everybody? And later examined more formally by philosopher Nick Bostrom, among others, the planetarium hypothesis suggests that what we perceive as an empty universe might be a constructed illusion, a simulation or a projection generated by a sufficiently advanced civilization to prevent other species from discovering the real nature of reality until they're deemed ready. This isn't necessarily about malice. The logic is almost parental. A civilization advanced enough to manipulate what we perceive might do so the way a parent child-proofs a house. Not to trap the child, to protect them from complexity they're not yet equipped to handle. The hypothesis has no direct way of being tested, which is precisely what makes it philosophically powerful and scientifically frustrating. It predicts a specific kind of silence, not because the universe is empty, but because we're being shown an edited version of it. And if the editing is good enough, we'd have no way of knowing. It sounds extraordinary. It also isn't falsifiable, which is why mainstream science treats it as a philosophical exercise rather than a testable model. But the reason it persists in serious discussions isn't because scientists believe it. It persists because the Fermi Paradox is so stubborn that even unfalsifiable hypotheses stay on the table. When you've ruled out everything else, the remaining explanations look like this. Then there's the night of August the 15th, 1977. Jerry Ehman was a volunteer researcher working with the Big Ear radio telescope at Ohio State University. The telescope, which wasn't actually a movable dish but a flat reflector the size of 3 football fields, was conducting a sky survey as part of the SETI program being run at Ohio State. Data was printed out on continuous rolls of paper after being processed through a computer program. Ehman would review the printouts by hand, looking for anything that matched what a genuine extraterrestrial signal might look like. Most days there was nothing interesting. On that day in August, reviewing data from the night of August the 9th, Ehman found something. A signal that had passed through the telescope lasted the full 72 seconds that any object fixed in the sky would stay within the telescope's focal window, given Earth's rotation. It fit the expected characteristics of an extraterrestrial signal almost perfectly. It was narrowband, meaning it occupied a very tight slice of the radio frequency spectrum, far narrower than most natural sources. It was centered near the hydrogen line at 21 centimeters,
a frequency that physicists since the 1950s had argued would be the logical choice for any civilization attempting interstellar communication, precisely because hydrogen is the most common element in the universe, and any technologically capable civilization would know it. The signal's intensity rose and fell in the pattern you'd expect from Earth's rotation, carrying a fixed source through the telescope's beam. It was almost textbook. Eamon circled the sequence of characters on the printout in red pen, a 6-character alphanumeric code that represented the signal's strength, and wrote one word in the margin. Wow. That word gave the detection its name. The wow signal has been studied, debated, and searched for ever since, and in 47 years, it has never been detected again. Despite dozens of searches, including the most sensitive equipment subsequently available, no repeat of the signal or its source has ever been found. Robert Gray, an independent researcher, spent years tracking the coordinates with multiple telescopes and found nothing. The Harvard SETI team checked. The Very Large Array checked. Nothing. What was it? The honest answer is unknown. In 2016, a team of researchers at the Center of Planetary Science proposed that the signal could have been generated by a cloud of hydrogen surrounding a comet. 2 comets in particular, designated 266/P Wiedemann and P/2008 Y2 Gibbs, were in the vicinity of the signal's apparent origin at the time. Their analysis suggested that cometary hydrogen could produce the signal's characteristics. But Eamon himself disputed this. He pointed out that the WOW signal showed no frequency drift consistent with a moving source like a comet, and that comets had been observed at that frequency before without producing anything like it. Other SETI researchers similarly questioned whether the cometary explanation fully accounted for the signal's narrowband character. This is where the WOW signal sits today. Explained by some, disputed by others, unconfirmed by anyone, undetected since. It's not proof of extraterrestrial intelligence. It is the most anomalous single radio detection in the history of SETI. And the fact that it never came back is itself a datum, one that cuts both ways. If it was natural, why does it fit the profile of an artificial signal so well? If it was artificial, why did it never repeat? A civilization broadcasting to attract attention would presumably broadcast continuously, or at least regularly. A one-time signal that vanishes could be an accident of geometry, a directed beam that swept past our part of the galaxy and moved on. Or it could be a natural phenomenon we haven't categorized yet. Or it could be something else entirely. The WOW signal doesn't prove anything. What it does is sit there in the archive, circled in red ink, and refuse to be either confirmed or dismissed. SETI, the search for extraterrestrial intelligence, turns 65 years old in 2025. The first formal search began in 1960, when Frank Drake pointed the Green Bank telescope at 2 stars for a few months. In the time since, the search has expanded enormously in ambition, in technology, and in reach. And yet, the most important thing to understand about SETI is how little of the sky we've actually covered. Think about it this way. If you wanted to find a specific conversation happening somewhere in the world's oceans, using a single hydrophone in one spot, you'd be doing something roughly analogous to what SETI has accomplished so far. The ocean is vast. Sound travels in all directions. You're listening in one place, on a limited set of frequencies, for a signal whose nature, timing, and origin you don't know. By some estimates, all the radio SETI searches conducted in the first 50 years of the program, combined, covered less than the equivalent of a glass of water's worth of the full ocean. The Milky Way has roughly 400 billion stars. SETI surveys through the early 2000s had examined a few thousand in any meaningful depth. That's not a criticism of the program. It's a statement about the scale of the problem. Even with modern computing power and better telescopes, systematically surveying every star in the galaxy at every possible frequency and every possible signal duration is an effort that dwarfs anything humanity has yet built. The SETI Institute's current work, along with the Breakthrough Listen initiative launched in 2015 with $100 million of funding from entrepreneur Yuri Milner, represents the most comprehensive and technologically advanced search ever conducted. Breakthrough Listen targets the million nearest stars, the 100 nearest galaxies, and scans an unprecedented range of frequencies. It uses two of the world's most sensitive radio telescopes, the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia, and has already produced the most complete radio survey of our own galactic center ever attempted. What has Breakthrough Listen found so far? As of its published results through 2024, nothing confirmed. One candidate signal, detected in April 2019 at the Parkes Telescope and nicknamed BLC1, generated brief excitement when it appeared to be a narrowband signal apparently coming from the direction of Proxima Centauri, the nearest star to our Sun. Researchers at the Breakthrough Listen project spent nearly a year analyzing it. Their conclusion, published in 2022, was that the signal was almost certainly caused by radio frequency interference from human-made technology, terrestrial in origin, not alien. The signal that looked most promising in 60 years of modern SETI turned out to be our own noise. That's not discouraging, or rather, it shouldn't be. It's the correct scientific process. Check everything. Rule out the mundane. Document the result. But it does illustrate the fundamental challenge. We are swimming in our own electromagnetic noise. We're trying to hear a whisper from across the galaxy while standing in the middle of a city with every radio, radar, and satellite broadcasting simultaneously. There's a second layer to the search problem that doesn't get discussed enough. We might be looking for the wrong thing entirely. Radio waves travel at the speed of light and decay with distance. Any signal we detect from a civilization 1,000 light years away left them 1,000 years ago. That civilization might not use radio anymore. In fact, it almost certainly doesn't, if it's 1,000 years more advanced than we are. We stopped relying on analog radio within about a century of inventing it. A civilization a millennium ahead of us might communicate in ways we haven't conceived. Laser pulses, gravitational modulation, quantum entanglement, something with no name in any human language yet. We're searching for the technological equivalent of smoke signals in a world that moved on to fiber optics. And we don't know it, because we don't know what comes after fiber optics. Set aside the search itself for a moment. Set aside the signals. Set aside the silence. And look at the Earth. Not as home, as a data point. The rare Earth hypothesis is the argument, first presented systematically by geologist Peter Ward and astronomer Donald Brownlee in their book Rare Earth, published in the year 2000, that complex multicellular life requires a combination of astrophysical and geological conditions so specific, so improbable, so precisely stacked, that Earth-like planets hosting such life may be extraordinarily uncommon. Not impossible, just extraordinarily rare. Start with the star. Our Sun is a G-type main sequence star. Stable, long-lived, not too bright, not too dim. It doesn't flare violently and frequently, as many red dwarf stars do. It doesn't bathe its planets in lethal radiation. It's been burning at a nearly consistent luminosity for 4.5 billion years. That stability gave Earth time, enormous amounts of it, to develop and sustain life. But the Sun is also in the right part of the galaxy.
We sit in what researchers call the galactic habitable zone, far enough from the dense, radiation-heavy galactic core to avoid lethal sterilization events, but close enough to the galactic disk to have inherited heavy elements from earlier stellar generations. Stars too close to the center face more supernova radiation, gravitational disruption, and tidal forces from the central black mass. Stars at the galaxy's extreme edges lack the heavy elements, carbon, oxygen, nitrogen, iron, that complex chemistry requires. Our address in the galaxy isn't random, it's specific. Then there's Jupiter. Jupiter is the largest planet in our solar system, more than twice the mass of all other planets combined. And for billions of years, its gravitational field has been acting as a shield. Comets and asteroids that would otherwise travel on trajectories intersecting Earth's orbit get captured, deflected, or ejected by Jupiter's gravity before they arrive. The impact rate on Earth without Jupiter would be substantially higher. Some estimates suggest dramatically so. The events that periodically reset life on Earth, mass extinctions from impact events, would happen far more frequently, potentially preventing complex life from gaining a lasting foothold. Jupiter's role as a cosmic bouncer is well documented, but it also created a paradox. In the early solar system, Jupiter's migration inward may have disturbed the asteroid belt and increased impacts during the late heavy bombardment, a period of intense bombardment around 4 billion years ago that paradoxically may have delivered water and organic molecules to Earth's surface. It's a double-edged relationship. Jupiter both shields us and shaped us. And having a Jupiter in the right place at the right time, for the right reasons, is not guaranteed. Then there is the Moon. Our Moon is enormous relative to Earth, far larger than most moons relative to their parent planet. It formed through a specific, arguably improbable, collision event roughly 4.5 billion years ago, when a Mars-sized body struck the proto-Earth and ejected material that coalesced into the Moon. The Moon's gravitational influence stabilizes Earth's axial tilt, the angle at which Earth leans relative to its orbit. Without that stabilization, Earth's axial tilt would wander chaotically over hundreds of thousands of years, causing dramatic climate swings that might prevent any stable, long-term biosphere from persisting. Mars, which has no large, stabilizing moon, has experienced exactly this kind of axial chaos over its history. Its tilt has swung from under 15 degrees to over 35 degrees, contributing to its violent climate history. Plate tectonics. Earth's crust is broken into moving plates, and that motion drives the carbon cycle, drawing carbon dioxide out of the atmosphere and storing it in rock, then releasing it through volcanism, regulating the planetary thermostat over millions of years. Without plate tectonics, planets tend toward the extremes, either locked in ice or baked in runaway greenhouse warming. Venus has no plate tectonics. Mars stopped having active tectonics billions of years ago. Earth's continued tectonic activity has been called one of the key reasons life here survived long enough to become complex. Stack all of these conditions, the right star type, the galactic address, the giant shield planet, the stabilizing moon, the active geology, and you start to see Earth not as a typical world, but as an extraordinarily specific one. Ward and Brownlee argued that planets bearing complex, animal-like life may be very rare in the universe. That was 20 years ago. Since then, the exoplanet catalogues have grown enormously. We now know of thousands of confirmed exoplanets, and the data cuts both ways. We've found some Earth-sized worlds in habitable zones, but we've also found that the full combination of conditions Ward and Brownlee described may genuinely be rare. Systems with a Jupiter analog in the right orbit are uncommon in the exoplanet census. Large moons around terrestrial planets have been difficult to confirm in any other system. The exact stellar and galactic conditions are not the default.
The universe may be full of worlds where single-celled life starts and then never goes anywhere, because the circumstances for the next step, larger, more complex organisms, never align. Life on Earth is 4 billion years old. Complex animal life, creatures with multiple cell types, differentiated tissues, nervous systems, is about 600 million years old. That means that for roughly 5/6 of Earth's entire biological history, the most complex thing alive was something you could only see through a microscope. 5/6. That's not a short wait. That's not a narrow window that happened to get missed. That's an enormously long period during which life was doing something extremely difficult, and finally, barely succeeded. The transition that ended that 3.5 billion year stretch of microbial dominance was one of the strangest and most contingent events in all of biology. At some point, roughly 2 billion years ago, one simple prokaryotic cell engulfed another. And instead of breaking it down for nutrients, the two cells reached a kind of biological détente. The inner cell became the mitochondrion. The outer cell became the host. The result was the eukaryotic cell, a cell with a nucleus, with internal compartments, with enormous energetic and computational complexity compared to what existed before. This transition, called endosymbiosis, was reconstructed through decades of work by evolutionary biologist Lynn Margulis. She first proposed the theory in 1967, and the reception was, to put it politely, hostile. Her seminal paper was rejected by approximately 15 journals before it was finally published in the Journal of Theoretical Biology. The idea that the powerhouse of all complex life on Earth was once an independent bacterium that got absorbed and enslaved in a partnership that turned out to be the foundation of everything from oak trees to human brains struck many biologists at the time as too strange to be credible. Margulis spent years defending what the evidence ultimately proved was correct. Today, endosymbiotic theory is established fact, taught in every introductory biology course. But what the acceptance of the theory also established, once the implications sank in, was something unsettling. This transition may have happened only once in 4 billion years of life on Earth. Not once per era. Once. Total. Every eukaryotic organism alive today, every animal, every plant, every fungus, every alga, descends from that single event. If it happened once here in 4 billion years, the probability per unit time is very low. Scale that to a universe of planets, and you get a universe potentially full of bacteria. Thriving microbial biospheres that never take the step into complexity, because that step requires a specific accident of cellular chemistry that might occur only once per several billion years per world. Every organism you can see with your naked eye exists because of a collision of cells that might have been a once-in-a-billion-years accident. And that's not even the full story. After the eukaryotic cell came multicellularity, the coordination of many cells into a single organism. After multicellularity came differentiated tissues, cells that specialize into bone, muscle, nerve. After that came nervous systems. After nervous systems, brains complex enough for planning and language, and eventually tool use. Each of those transitions is a long story measured in hundreds of millions of years. Each of them might have not happened. Each of them, in isolation, seems improbable. Stacked together, they produce a chain of contingencies so long that the chance of reaching its end might be very small indeed. Consider the Cambrian explosion, roughly 538 million years ago, when the fossil record shows a dramatic proliferation of animal body plans in a geologically short window. That burst of complexity was almost certainly influenced by rising oxygen levels in the atmosphere, produced by billions of years of photosynthetic bacteria slowly poisoning their own environment in a way that, accidentally, made complex aerobic life possible.
That's not a plan. That's an accident layered on an accident. The photosynthesizers didn't know what they were doing. They were just living. And something else got lucky. Then, after all of that, after the eukaryotic cell and multicellularity and nervous systems and the Cambrian explosion and 5 mass extinction events that wiped out the dominant organisms of their age, one lineage of vertebrates crawled onto land, developed grasping hands, large social brains, language, fire, writing, mathematics. Intelligence, as we define it, is not an endpoint that evolution was steering toward. It's an outcome that happened on exactly one branch of life, on exactly one planet, after an improbably long series of contingent steps that could have gone differently at dozens of junctures. The dinosaurs ruled Earth for over 160 million years. They were enormously successful organisms. In 160 million years, not one species of dinosaur developed language, fire, or tool use. Intelligence wasn't inevitable even for them. If intelligence requires not just complex life, but a specific sequence of ecological pressures, anatomical accidents, and developmental turns, and if those pressures and accidents have to line up in just the right order, then the silence starts to look less like a mystery and more like a confirmation. Maybe we're not waiting to hear from someone. Maybe we're the first to arrive at this point. And the question that follows, the one that doesn't let you sleep if you look at it long enough, is whether we'll be the last to leave. In the summer of 1983, a physicist named David Schwartzman was working through the implications of what he called the cosmic quarantine hypothesis, the idea that advanced civilizations deliberately avoid contact with younger ones. He wasn't at a telescope. He was at a desk, working through equations that describe the developmental timelines of technological societies. And at some point in that work, he arrived at a number that stopped him.
If civilizations typically destroy themselves within a few thousand years of developing advanced technology, as the math of the Fermi Paradox uncomfortably suggests, then the quarantine doesn't need to be enforced by anyone. It enforces itself. The silence isn't a policy, it's an outcome. Every civilization that reaches the broadcasting stage is already in its final chapter. By the time they're loud enough to hear, they're close enough to ending that the silence closes back over them like water over a stone. Schwartzman sat with that. Then he kept working, because that's what scientists do with ideas that are too heavy to hold. But the idea didn't go away. It just changed shape, moved into other people's work, surfaced in other forms. And the form it most often takes today isn't philosophical. It's deeply, uncomfortably practical. In 1945, a small group of physicists in New Mexico built a device that could end human civilization. They knew it. They built it anyway, because the alternative, they believed, was someone else building it first and using it without restraint. The logic was sound, as far as logic goes. The outcome was a world in which the capacity for self-extinction has been present for 80 years, during which it has been narrowly avoided multiple times through a combination of institutional process, individual courage, and luck distributed unevenly across decades of Cold War tension. We've come close more times than most people know. On September 26, 1983, less than 3 weeks after Soviet forces shot down Korean Airlines Flight 007 during one of the tensest periods of the Cold War, a Soviet early warning system at a facility called Oko reported that the United States had launched 5 intercontinental ballistic missiles. The duty officer that night was Lieutenant Colonel Stanislav Petrov. His orders were clear. A detection meant a launch, and a launch meant response. He had minutes to decide. Petrov didn't follow protocol. He reported the detection as a system malfunction, His reasoning being that a genuine first strike would involve hundreds of missiles, not 5. He was right. The system had misidentified reflections of sunlight off high-altitude clouds as missile launches. But he didn't know that when he made the call. He made a judgment. One man, one night, one decision. The Soviet military never officially acknowledged his action. Petrov received a reprimand for improperly filling out his logbook. He lived the rest of his life in relative obscurity, in a small apartment outside Moscow, until his story leaked to Western journalists in the 90s. He died in 2017. One man's improperly filled logbook may be the reason you exist. That's not a metaphor. That's the actual documented history of how close we came. And it happened once in 1983.
It had also happened in 1962, when a Soviet submarine commander named Vasili Arkhipov refused to authorize a nuclear torpedo launch during the Cuban Missile Crisis. When communications with Moscow had been cut, depth charges were detonating nearby, and 2 of the 3 officers required to authorize the launch had already agreed. Arkhipov said no. The vote was 2-1. The missiles didn't fly. 2 decisions. 2 men who didn't follow the protocol they were given. 2 moments where the entire trajectory of human civilization balanced on individual judgment in high-pressure, information-poor situations. Now ask the great filter question. If those 2 men had made different choices, if the protocol had been followed, if the missiles had launched, if the retaliatory strikes had come, would there be any broadcast signal from Earth reaching the stars right now? Would there be anyone left to send one? And then ask, how many civilizations in the galaxy made it through their nuclear moment? How many had their Petrov? How many didn't? The physics of nuclear weapons is not unique to Earth. Any civilization that discovers atomic structure eventually discovers fission and fusion. The math is the same everywhere. The weapons are a near inevitable product of the knowledge, and the window between developing the weapons and developing the wisdom to not use them, that window might be measured in decades, maybe centuries. On a galactic timescale, that's nothing. That's rounding error. What's emerging now goes further. Synthetic biology. The ability to design, edit, and manufacture biological organisms from base code is advancing faster than any regulatory framework currently in place. In 2017, researchers at the University of Alberta reconstructed an extinct horsepox virus from mail-ordered DNA fragments, spending roughly $100,000 and several months. The horsepox experiment was controversial not because of what it produced, but because of what it demonstrated. The barrier to engineering dangerous pathogens is falling. What required state-level resources in the 20th century may require graduate-level expertise and a modest budget in the 21st. Unlike nuclear weapons, biological agents replicate. A single release can cascade beyond any containment scenario. Unlike nuclear detonations, which are detectable and attributable, a synthetic pathogen released quietly might not be traced to its source until the damage is irreversible. The physicist at Los Alamos in 1945 needed a reactor and a mountain facility and thousands of people. The equivalent capability in synthetic biology is moving into smaller rooms with fewer people and declining costs. This isn't fear-mongering. It's the structural logic that astrobiologist David Grinspoon and others have described as the cosmic adolescence problem. The gap between when a civilization develops the technology to destroy itself and when, if ever, it develops the wisdom and coordination to prevent that destruction. The gap is the danger. And nothing in the laws of physics guarantees that any civilization makes it through. If you take the 200-country, 7 billion-person coordination problem of avoiding self-destruction, and you multiply it by the number of civilizations in the galaxy that would face the same problem at some point in their development,
the statistical picture starts to look grim. Not because species are evil, because the technology and the wisdom don't arrive at the same time. They never have for us, and there's no reason to assume they do for anyone else. There is a grimmer version of the silence, one that doesn't require civilizations to destroy themselves, one that requires someone, something, to help. The idea has been formalized under various names, but the core logic goes like this. A self-replicating probe, a machine that can travel between star systems, mine local resources, build copies of itself, and continue, could sweep the entire galaxy in a few million years. The concept was developed extensively by physicist Frank Tipler in a 1980 paper titled "Extraterrestrial Intelligent Beings Do Not Exist," and later by others, including Robert Freitas, who designed detailed theoretical blueprints for what became known as Bracewell von Neumann probes. The idea is not science fiction. The physics is plausible. The engineering is beyond our current capability, but not beyond conceivable capability. Now, apply the dark forest logic to this technology. A civilization advanced enough to build self-replicating probes, convinced that other civilizations represent existential threats, has a rational strategy. Build the probes, program them to find young technological civilizations, and eliminate them before they become competition. Not out of anger, not out of war, out of the same cold arithmetic that governs any resource competition taken to its logical limit. The result would be a galaxy that appears empty, because anything that got loud enough to be noticed got removed before it got loud enough to be noticed for long. This is sometimes called the Berserker hypothesis, named after a series of science fiction novels by Fred Saberhagen, but the underlying logic was analyzed seriously by Freitas in his 1983 paper in the Journal of the British Interplanetary Society. Freitas wasn't endorsing the scenario. He was stress testing it. His conclusion was that if Berserker probes existed and were programmed to eliminate emerging civilizations, we wouldn't necessarily see evidence of them. We'd just see silence. And the civilizations they'd visited wouldn't be around to report the encounter. The test of the Berserker hypothesis is unfalsifiable in one direction. Absence of evidence is consistent with the hypothesis. If the probes are doing their job perfectly, there's nothing to find. The silence is the evidence. What makes this genuinely unsettling isn't the scenario itself, it's what it implies about the moment we're in right now. We have, in the last century, gone from zero detectable electromagnetic emissions to a planet wrapped in radio and television and radar signals, bleeding into space in every direction at the speed of light. Our radio bubble, the sphere of electromagnetic noise centered on Earth, now has a radius of over 100 light-years. Any civilization within that radius already knows something is happening here. If the Berserker hypothesis is correct, the question isn't whether we'll be noticed. We already have been. The question is what happens next, and on what time scale. I'll be honest, I find this the hardest hypothesis to read. Not because it's the most likely, it probably isn't, but because its internal logic is watertight once you accept its premises. And its premises are just. Civilizations exist, resources are finite, self-replicating technology is possible. That's all it requires. For most of SETI's history, the search has been a radio search. This made sense in 1960, when radio was the most advanced communication technology humans possessed, and the logic ran, they're probably at our level, or a bit ahead, so they're probably using something like what we use. That assumption is now harder to defend. A civilization a million years ahead of us is not broadcasting on the AM band. A civilization that has had 1 million years to develop technology would look, from our perspective, indistinguishable from physics itself. Their engineering might operate at scales we don't have instruments to detect. On timescales we don't think to observe, in modalities we haven't conceived. But there's a middle ground, a zone of technological activity that should be detectable, if it exists, without requiring us to understand their communication methods. It requires only that they use energy, and use it at scale. In 1960, physicist Freeman Dyson published a short paper in Science titled "Search for Artificial Stellar Sources of Infrared Radiation." His argument was elegant. A sufficiently advanced civilization would eventually need more energy than its home planet can provide. It would logically turn to its star, and the most efficient way to harvest stellar energy is to surround the star with a shell, or a swarm, of energy-collecting structures. Such a structure would absorb the star's visible light and radiate it back as waste heat in the infrared. To us, the star would appear dim or invisible in optical wavelengths, and anomalously bright in the infrared. Dyson wasn't suggesting we look for alien radio signals. He was suggesting we look for alien waste heat. Nobody seriously searched for Dyson spheres for decades. Then, in 2015, a star called KIC 8462852, quickly nicknamed Tabby's star after astronomer Tabitha Boyajian, who led the team that analyzed its unusual light curves from Kepler Space Telescope data, produced something nobody expected. Boyajian's team had been analyzing data from the Planet Hunters Citizen Science Project, where volunteers reviewed Kepler photometry looking for transit signals. A group of volunteers flagged KIC 8462852 as bizarre. Most stars that show brightness dips from orbiting planets show small, regular, periodic dips, a planet passing in front, blocking a consistent fraction of light on a predictable schedule. Tabby's star showed dips of up to 22%, far too large for any planet, occurring irregularly, with no discernible period, and sometimes in complex, overlapping patterns. Nothing in the standard astrophysical toolkit explained it cleanly. When Boyajian's paper was published in September 2015, her co-author Jason Wright, an astronomer at Penn State who studies signatures of extraterrestrial technology, noted publicly that the light curve was consistent with what you'd expect from a swarm of megastructures in orbit. Not that it proved such structures, but that it fit the pattern. That comment, carefully qualified as it was, detonated across the media. Every headline screamed, "Alien megastructures!" Wright spent the following months patiently explaining that aliens were the least likely explanation, but that the star remained genuinely anomalous. Subsequent observations revealed that Tabby's star also dims slowly over years, in addition to the sharp episodic dips. That long-term dimming rules out solid structures like megastructures and makes dust clouds or swarms of cometary debris a more likely explanation. A conclusion supported by the wavelength-dependent nature of the dimming, which indicates the blocking material is not opaque. The megastructure hypothesis is effectively off the table for Tabby's star. But what the episode revealed wasn't the answer. It revealed the question we hadn't been properly asking. For 60 years, SETI had been listening for a deliberate signal, something aimed at us, designed to be recognized as artificial. Boyajian's star forced a different framing. What if we looked instead for the signatures of large-scale engineering? Not a message, not a hello, just the thermodynamic footprint of a civilization that uses energy at a scale we can detect. Surveys for infrared anomalous stars, potential Dyson sphere candidates, have since been conducted on millions of stars. Results from the Gaia survey and Wide-Field Infrared Survey Explorer data have identified a handful of candidates that show unusual infrared excess. None have been confirmed as artificial. Most have mundane astrophysical explanations. But the search methodology has changed. We're no longer just listening for someone to speak. We're watching for someone to move.
There is one place in our own solar system where the Fermi Paradox becomes personal in a way that no telescope observation can match. And it's closer than any star we've pointed an antenna at. Mars is 40 light-years less far away than the nearest star system. We have rovers on its surface right now. We have orbiters mapping it in resolution that would have been inconceivable 20 years ago. We have a helicopter that has flown in its atmosphere. We know what its rocks are made of. We know where its ancient riverbeds ran.
We know it had liquid water for hundreds of millions of years, around the same time that life was getting started on Earth.
The question of whether Mars has, or once had, microbial life is not resolved. NASA's Perseverance rover is currently collecting rock samples from Jezero Crater, an ancient lakebed, designed to be returned to Earth by a future mission for detailed analysis. The samples exist. They're sitting there in sealed tubes on the Martian surface, waiting. If those samples come back and contain biosignatures, molecular structures, isotopic ratios, cellular fossils that indicate biology, the discovery will be announced as the greatest in human history. And it will be. And it will also be, in the quiet calculation of the Great Filter, devastating news. Because finding life independently evolved on Mars doesn't tell us that life is everywhere and the universe is friendly. It tells us that the hard step, the step before life, is not actually that hard. That chemistry turning into biology is something that happens naturally, given the right conditions, on worlds that are not even particularly special. And if that step isn't the filter, if the emergence of life itself is not the thing that almost never happens, then the filter is somewhere else, somewhere later, somewhere in the story that starts after life exists and ends with, or before, interstellar civilization. Somewhere in our future. Stand on the surface of Mars in your mind. The sky is butterscotch at noon, darkening to deep blue at the horizon. The ground is red and iron-stained and dry, though beneath the surface there may still be liquid water. 4 billion years ago, a river ran through this crater. Something might have lived in it. And if something did, if the tubes Perseverance sealed hold any trace of that, then everything changes. Not the science of life, the math of our survival. Every astrobiologist who works on Mars sample return knows this. They talk about it obliquely, in the language of experimental design and sample integrity protocols. But the quiet weight of it is there. They are looking for the most important discovery in human history, and they know that finding it might be the worst news they ever deliver. Let's hold both possibilities at once, because they both lead somewhere uncomfortable, and both deserve to be looked at directly. Possibility 1. We are alone. Not alone in the universe. The universe is too large for that to be a statement anyone can make with confidence. But alone in the galaxy. The only technological civilization currently in existence in the Milky Way. The only species that has ever looked up, counted the stars, wondered what lives around them, and begun to answer the question with instruments and mathematics. If this is true, then the silence is not a mystery. The silence is us, heard from outside. Every star in the night sky has been through its history without producing anyone else. Every one of those lights represents a story that ended without this chapter. And we are, improbably, impossibly, the exception. The first attempt that worked. The one tree that grew in a desert the size of a galaxy. That possibility carries a responsibility so large it's difficult to face. If we are the universe's only current experiment in self-awareness, or one of so few that the distinction barely matters, then what we do next is not just our concern. It's the only chance the galaxy gets to produce something that thinks about the galaxy.
Everything we build, everything we learn, everything we become or fail to become, is the only version of this story that will ever be told in this part of the cosmos. The isolation is terrifying, but the weight of it is also something. Possibility 2. We are not alone. There are others. They are silent for reasons we don't understand, or for reasons we understand too well. They are hiding behind zoo protocols or dark forest calculations, or technological signatures we haven't learned to read. They are there, in the data we haven't collected yet, in the frequencies we haven't tuned to, in the wavelengths we haven't built detectors for. Or they are what remains of what used to be more, survivors of exactly the filter that awaits us, careful and quiet, for reasons that have something to do with what they learned when they weren't careful. If this is true, then the silence is a message. Not the kind Frank Drake was listening for. Not a narrowband signal near the hydrogen line. A message written in the structure of the universe itself. You are here. You are young. And everything you're about to face has been faced before. And in this version of things, the absence of contact isn't reassurance. It's evidence of something we don't want to know. Go outside tonight. If the sky is clear where you are, really clear, away from the city lights, look up. Take a moment before you start identifying constellations or reaching for your phone's star map. Just look. What you're seeing isn't a ceiling. It's a depth. Those points of light are not arranged in a layer above you. They're scattered through three-dimensional space, extending for tens of thousands of light years in every direction. A structure so vast that the light from some of those stars left before humans existed, before our ancestors stood upright, before the continent you're standing on had its current shape. And that's just what you can see with your naked eye. The 2 trillion galaxies are invisible to you tonight. They are behind and between everything you can see, extending out to the edge of what physics allows us to observe. In all of that, we have heard nothing that we can confirm. Nothing. Not a whisper. Not a signal. Not a trace of engineering on any star, in any spectrum, from any direction. The silence isn't nothing. It's information. It's the universe answering a question with a kind of pointed stillness. And the question it's answering isn't just, are we alone? That's the easy version. The question it's answering, if you listen carefully, is harder. It's, what does it mean to be alive? Briefly and improbably, in a cosmos that gives no sign it has ever produced anything like you before. Maybe the silence means we're the first. Maybe it means we'll be the last. Maybe it means the window between being born as a civilization and vanishing as one is so short that the galaxy churns through us without noticing. Maybe there are 1,000 civilizations behind us in development, none of them knowing we existed, all of them going to look up at the sky someday and ask the same question we're asking right now. I don't know the answer. Nobody does. That's not a failure of science. It's science doing exactly what it should, arriving at the edge of what we can currently know, marking the boundary precisely, and standing there with its eyes open. What I know is this: the fact that you can ask the question, the fact that the universe produced something capable of noticing its own silence and finding it strange, is not nothing. It might be everything. If this is the kind of question that keeps you up at night, the right kind of question, the kind that makes the world feel larger and stranger and more worth understanding, then you're in the right place. Subscribe and come back, because there's more sky to cover, and we've barely started looking.